kind of specificity that, that makes it bind to genes with relatively few exons. Or at least I'm pretty sure it does, because only 1% of the time would that have happened by random chance alone. Now, I'd like to note, what we'd really like to do, we'd like to try out every single possible set of 15 genes from the human genome. Because then that would really tell us. It wouldn't be, oh, well, you know, this simulation we did it 5,000 times, and you know, it's 1% this time, and you know, maybe it's 2.5% next time, or 0.3% the time after that. You know, what we'd really like to do is do every single possible set of 15,000 genes, or 15 genes in the human genome, and then we would know exactly how likely that is. It turns out there's a lot of 15 possible genes from 60,000 odd genes. And okay, right, the human genome doesn't have 60,000 protein coding genes. The table that we downloaded has a different column for each isoform, so 60,000 protein coding isoforms. So that would take a long time to enumerate all of them. So we're just going to take a random sample of 5,000 of the possible sets and assume that it's probably close enough. Okay. So again, we've seen the power of simulation to answer a question in a pretty straightforward manner. It turns out we can answer this question with math, and if you know that the hypergeometric distribution gives you the result of number of trials of successes without replacement from some ball and urn problem, and you can think, well, this looks like a ball and urn problem, and you know, you can open your stats textbook, and we could have solved this without having to do the simulation. But we didn't have to open the stats textbook. We just wrote a few lines of code to ask the exact question we wanted to ask. And sometimes the questions that you want to ask aren't well modeled by a problem that involves balls and urns. And so having the simulation tools gives you the ability to ask those kind of questions. So, okay, this is a little dry and kind of bioinformatics-y. You know, what if you're not a what if you're not a gene jockey? What if this totally is not interesting to you? What if what you want to do in life is to give mice cancer? Or, you know, maybe keep them from getting cancer. I guess that's probably what you want to do in life, if you want to study cancer in mice. So is all this stuff even relevant if you want to study cancer in mice? And we're not talking about drawing genes out of the human genome. Yes, I wouldn't ask the question if it wasn't totally relevant. So let's say that you have a pilot grant from the National Blueberry Council to test if blueberry extract prevents cancer. This is a pilot grant. Blueberry extract is expensive, so we set up the experiment with this. We've got 15 mice. On regular chow, RRC. And like I said, blueberry extract, expensive. We can only afford to put 10 mice on blueberry chow. And we do the experiment, and you know, mice are little cancer factories. So this is the result we get. We have regular chow, blueberry chow, yes cancer, no cancer. And we get only 3 of our regular chow mice got cancer. But 4 out of our 10 blueberry mice failed to get cancer. So, in this column, we've got 80% of them have cancer, obviously 20%. This column, %60 have cancer and 40% don't have cancer. Now the National Blueberry Council has been calling you up like every day for the last 6 months because they want to know the results of your mouse study. And they have, you know, you told them those results and they've divided these numbers, all the different ways they can divide them, and they've found the biggest number from dividing these different numbers. So they are going to put out a press release that says, blueberries make you twice as likely to be cancer-free, which I guess is correct. Or maybe they're going to put out a press release, not eating blueberries makes you 33% more likely to get cancer. That sounds like a good press release, right? So what you want to know is, do you need to call them up and tell them to take your name off that press release? Okay, so how are we going to answer this question? We're gonna simulate. Because I am simple-minded, and I like to write out on computer code what I'm going to do and what question I'm going to ask, and we're just going to see what the answer is. So really the fundamental question we want to know is, okay, like, you know, we think that the probability of blueberry eating and having cancer is not independent. You know, we think that the blueberry eating is doing something to our probability of getting cancer. That's what the Blueberry Council sure wants to hear. But what if we're wrong? What if cancer were independent of blueberries? So let's write that out. Independence, probability. Remember, this is our definition of statistical independence. The probability of eating blueberries and having cancer is just the same thing as the probability of eating blueberries times the probability of having cancer. So we want to test, what if this is true? What if this is independent? How likely would we be to see 4 mice cancer-free if this was true? Well, we can simulate that. But let's think for a second. Do we really want to know exactly the probability of getting exactly 4 mice cancer-free? Not really. You know, what if we were super rich and we did a 1,000 mouse trial and we got 400 mice that were cancer-free? And you know, should we set up our simulation? Well, what's the probability of getting exactly 400 cancer-free mice? I mean, that's probably going to be a relatively low number. Even if you're flipping a fair coin, if you flip that fair coin, you know, 1,000 times, you're pretty unlikely to get exactly 500 heads and exactly 500 tails. So the question we really want to ask has to do with probability areas. Remember, when we're talking about probabilities, we want to think about the areas, not sort of point estimates. So what's the relevant area? Well, we want to know that the first thing we might want to ask is, okay, what's the probability of getting 4 or more cancer-free mice in the blueberry group if exactly 7 mice total were cancer-free? This seems like a plausible way of setting up this problem. So, okay, 7 cancer-free mice. So that's this, or 1 minus that. Probability of blueberry eating is 10 out of 25. So what's the probability of getting 4 or more from this kind of trial? Let's simulate that. Okay, so the first thing I need to do, I'm going to make this like really straightforward. Just going to have a list of mice. So some are eating regular chow, 15 are eating regular chow. So this thing, okay, this is a list that contains just one element called with the string RC, and we're going to repeat that 15 times. So you can multiply lists. And that repeats them. And you can add lists, and that sticks them together. So, all right. So let's make sure this actually works. This should be a list of 15 RCs followed by 10 BCs. Yep. So these are the chow labels for our 15 different mice. Okay. So what if we choose 7 mice from our set at random to be cancer-free? Okay, we know how to do that. All right, we're going to choose 7 without replacement. Obviously, we're choosing them to be cancer-free. We can't put them back. And this gives us, okay, you know, some of the mice are R's and some of them are B's. Right? This is what you would expect. Okay, so now let's count up, out of 10,000 trials, what's the probability of 4 or more of the cancer-free mice being blueberry eaters? Okay, so count equals 0 for I am range 10,000, and after this we're going to take a little break. Okay, so what do? All right, so the no cancer mice, the ones that we're choosing randomly to be cancer-free, is we're just going to choose 7 mice randomly to be cancer-free. Seem reasonable? Everyone on board with this? And I mean, we're not doing this. This is sort of the hand of fate that's guiding the cancer to our mice, independently of whether or not they ate blueberry. We're just choosing 7 mice from our whole population at random. All right, so now we want to know how many of those 7 ate blueberries. So we're gonna, okay, let's just go through the no cancer mice and sum up how many ate blueberries. So 4. So remember, this no cancer mice list is just going to be a list of BCs or RCs. So for mouse and the no cancer mice, if its food label is BC, well then we're going to say it was a blueberry eater. So we're going to add 1 to the total of blueberry eating. Okay, so now we've totaled up how many ate blueberries. So if more than 4 of them ate blueberries, colon. So if more than 4 by random choice were blueberry eaters, we're going to add this to our count of the number of times this thing would happen, just totally random, if there was no relationship between blueberry eating and mouse cancer. Does everyone buy that this simulation is basically going to do what we want? Any questions about it?
On the line for mouse and no cancer, why should it just be no cancer?
Oh, yeah. Thank you. Okay, then what we're going to do is what we've always been doing, right? What's the fraction that happens? So let's run that. Oh my! 26% of the time, we got 4 or more cancer-free mice, even if there was no relationship between cancer and blueberry eating. So, you know, now we should be thinking, all right, maybe we should call that Blueberry Council and tell them to hole up a little bit. But, you know, 4 or more is not the only kind of crazy result that we could have gotten by random chance. On the break, we'll take a 3-minute break. After the break, we'll talk about other ways that we might set up this probability to give us a more realistic estimate of how surprised we ought to be. So let's break for 3 minutes.